Hello students! So, let's remember what the previous video was, because this represents an optional follow-up to it. So in the previous section, we proved the extreme value theorem holds as long as you study continuous functions on closed bounded intervals. In fact, the extreme value theorem holds over a much larger class of sets, namely, any that class is compact sets. So somehow compact is like a good analytic analog of finiteness. And we'll kind of see what that means in this packet. So definition. A set is called compact if two things happen. One, if K is bounded. Certainly if you want a set to be analogous to a finite set, then it should be bounded. And the other property is that every limit point of the set K must be in K. That's what it means for a set to be compact. A set satisfying the second condition is called closed. So if a set contains every one of its limit points, then that set is closed. Let's go off to the side and remind ourselves what a limit point is. So P is a limit point of a set, well, it's called K over there, but I'll be generic, I'll call it X, means for every delta bigger than 0, there exists some point in X such that 0 is less than the absolute value of X minus P is less than delta. So pictorially, there's the real number line, there's the point P. If you go left to P minus delta and right to P plus delta, there is some point in there there's some point in the set big X inside of that open interval, and that thing is different from P. So there's the definition. We also came up with this reformulation. A reformulation of the definition of what it means to be a limit point says that a point is a limit point if there exists a sequence X sub n of elements of X different from P such that X sub n converges to P. So the picture in this case is there's the real number line, there's P. There should be a sequence worth of things in X that get close to P. So here's the actual extreme value theorem. The real extreme value theorem says, let K, a subset of R, be a non-empty compact set. Let F from K to R be a continuous function. Then the supremum of F of K and the infimum of F of K each exist and are elements of K. And you'll notice that's exactly the same thing as we stated as the extreme value theorem over a closed bounded interval I, except now instead of assuming that K is a closed bounded interval, K is assumed to be compact. And let's start by just understanding what compact even means. So are these sets closed, bounded, compact? Well, the interval the interval from 1 to infinity is obviously not bounded above. So it's clear it can't be compact, because to be compact it has to be both. I claim it is closed. And you've proven something a lot like that in the past. In fact, it's a pretty straightforward exercise. Maybe we'll explore why right here. Why? Well, let's let P be a limit point. And let's use this sequential reformulation because I'm going to use that all over the place. So there exists a sequence xn of elements of 1 to infinity with xn converging to p. Well, the fact that xn is in the interval from 1 to infinity means 1 is less than or equal to xn. So by limit laws, 1 is less than or equal to the limit of xn, namely p. So p is in the interval from 1 to infinity. So I started by considering any limit point and concluded that limit point was in the original set. So that means that the interval from 1 to infinity is closed. But it's not bounded, and a compact set has to be bounded. A compact set is simultaneously bounded and closed. So this set is not compact. The second one, the interval from 0 to 1, well, it is bounded. It's bounded by 0 below and 1 above. It is not closed. And let's see why. Well, maybe it's easy to see why by looking at a picture. So let's draw that set. So there's it's the set excluding 0, including 1. Well, if you look at 0, there's stuff in the set that's real close to 0, but 0 is not in the set. So this is a limit point of the set, which is not in the set. 0 is a limit point, but it is not in the set, the interval from 0 to 1. So this set does not include every one of its limit points. It's missing one limit point. So B is not closed. Very nice. So here's the first main theorem of today. Every closed bounded interval is compact. So let's consider any closed bounded interval. Let's let A be less than B. Let's consider the interval from A to B. I claim that it is compact. To show that it is compact, we want to show A comma B is bounded and closed. Well, boundedness is obvious, right? A is a lower bound, B is an upper bound. Maybe we'll just be rigorous about it. So let's explain why A comma B is bounded. We will show A is a lower bound and B is an upper bound. So let's do that. Let's consider any. X in A comma B. Then by the very definition of that interval, well, let's see, we considered any x in the set and concluded the inequality that we needed. Thus, A is a lower bound, B is an upper bound. Nice. So it's bounded. Let's show that it's closed. So to show us that it's closed, we need to show it contains every one of its limit points. So let's do that. Let's let P be a limit point of the closed interval from A to B. I need to show, sorry, let's put that. Want to show P is in A comma B. So what does that mean? I want to show that P is in the interval from A to B, then I want to show that A is less than or equal to P is less than or equal to B. So let's try to do that. Let's let P be a limit point of the closed bounded interval from A to B. By the reformulation of limit points in terms of sequences, there is a sequence xn such that, well, xn is a sequence of elements of that set, such that for all n in n, xn is in A comma B, and xn is not equal to P. Moreover, the sequence needs to converge to P. So we get a sequence xn, which is always in the interval from A to B, which is never itself equal to P, but which converges to P. And there's my goal. Well, this P is itself the limit of xn, and I certainly know that xn is somewhere between B and A, so it looks like I can just use the limit law that says that I can take an inequality and pass it to the limit to get the desired result. So let's do that. Let's let xn be in the interval from A to B. For every n in the natural numbers, I get the inequality that A is less than or equal to xn is less than or equal to B because of this fact, which is exactly that fact. So that just follows by how the sequence is defined. Passing to the limit, and remember, xn converges to P, we get that A is less than or equal to P is less than or equal to B, so that P itself is in the closed interval from A to B. So let's just analyze what we did here. We considered any limit point of AB. We said let P be a limit point of AB, and that's the only thing we ever assumed about P. We showed that P is in AB. So we can conclude that AB contains every one of its limit points. That's exactly what it means to be closed. As we've shown that AB is bounded and closed, the closed interval from A to B is compact. So that doesn't give you a reason to care about compactness, but at the very least, that means that if we can prove something is true about every compact set, then we will know that that something is true about every closed bounded interval. All right, so let's study compact sets. So I'm going to get a reformulation of compactness, and it won't be that deep. It'll be a reformulation that lets me just study sequences instead. So I have all of this language about how I can reformulate stuff in terms of sequences, so I'd like to use it. Right, I have a reformulation of continuity in terms of sequences and of limit points in terms of sequences. So I'll reformulate compactness in terms of sequences. Let's let K be a subset of R. K is compact if and only if, for every sequence x sub n of elements of K, there exists a subsequence x sub n sub K of x sub n, which converges to an element of K. So this is an if and only if. I want to show that this is true if and only if this is true. Well, let's go through that proof. So the forward direction first. So let's suppose that the set K is compact. So what does compact mean? If we assume that K is compact, then K is bounded and K is closed. Let's write down what we need to prove. I want to show that, I'm going to write fairly small, for every sequence xn of elements of K, x sub n has a subsequence x sub n sub K with limit x sub n sub K in the set big K. So I wrote small, but that went over the edge. Maybe I should have more space there. There's what I need to show. And the fact that that's written as a very quantified thing tells me how the proof should begin. I want to prove something is true for every sequence xn of elements of k. So let's let xn be a sequence of elements of k. What do I want to show? I want to show that xn has a subsequence which converges to an element of k, and that should give you ideas. What types of sequences have convergent subsequences? Well, by the Bolzano-Weierstrass theorem, bounded sequences have convergent subsequences. So let's start by showing that xn is bounded. Once we do that, we can appeal to the Bolzano-Weierstrass theorem. So let's do this. And maybe let's sketch the argument a little bit more just verbally. So the set K itself is certainly bounded. And every xn is an element of K. So that means that whatever bounds work for K should work for xn also. So I think there's the idea of the proof. Let's just write it down. So let's see. As K is bounded, it is ambiguous. K has an upper bound, U, and a lower bound, L, comma, L. Oh, and I don't want to use capital L's. Capitals should be resolved for sets. A lower bound, little l. I claim that these should be bounds on the sequence xn, so let's prove that. So let's consider any n in n. Well, this is a sequence of elements of k. So certainly each one of these xn's is an element of k. So that, let's see, this thing is an element of k, this is an upper bound, that's a lower bound. So I conclude that L is less than or equal to xn is less than or equal to u. Thus, u and L are bounds for the sequence xn. So the sequence is bounded. Since the sequence is bounded, I can use the Bolzano-Weierstrass theorem to conclude that x sub n has a convergent subsequence. Well, let's let x sub n sub k be that convergent subsequence, and let's let x be its limit. Well, I'm pretty close. Right, what do I need to show? I need to show that for every sequence x sub n of elements of k, x sub n has a subsequence x sub n sub k, which converges and whose limit is in k. And what do I have right now? Well, I considered any subsequence, so I'm proving something is true for every sequence x sub n of elements of k. I found that there exists a subsequence which converges. All I need to show is show that the limit is in the set k. So let's do that. Let's let x sub n be that convergent subsequence. Let's let x be its limit. I'm nearly done. All I need to show is that x is in k. Well, so let's suppose for the sake of contradiction that x is not in k. So I'm proceeding by contradiction. Well, I certainly have that for every natural number n, x sub n is in k. So that means that for every natural number k, x sub n sub k is in k. Well, if x sub n sub k is in k, and x is not in k, then x and k certainly cannot be equal. Because this is not in k, this is in k. So they have a property not in common, so they can't be the same. Oh, neat. So let's see what we found. We have now found a sequence x sub n sub k of elements of k which are not equal to x and that sequence converges to x. Oh, but check it out. That's exactly what it means to be a limit point, right? To be a limit point, you just need to have a sequence x sub n of elements of x different from the thing that they're converging to. Different from, well, p or itr, but k, such that x sub n converges to k. So by the sequential reformulation of limit points, this means that x is a limit point of k. Wait, k is compact. Compact sets are closed. By assumption, compact means closed and bounded. So I can conclude that x is in k. Why is this a contradiction? Well, the conclusion x is in k contradicts the assumption that x is not in k. So it must be that x, which recall is the limit of x sub n sub k, is in k. Now let's just summarize what we've done. Thus, well, if you look early in the proof, we started by considering any sequence of elements of k. We considered any sequence of elements of k. So, thus, for any sequence x sub n of elements of k, we produced a convergent subsequence. There exists a subsequence x sub n sub k whose limit is in k. Neato. That's exactly what we wanted to prove, so that completes the proof. This completes half of the proof. I still need to do the reverse implication. So let's go the opposite direction. Let's assume the thing in green. Let's assume that for every sequence x sub n of elements of k, there exists a subsequence of x sub n which converges to an element of k. So let's assume that for every sequence x sub n of elements of k, there exists a subsequence which converges, but not just converges, which converges to an element of k. So there's what I get to assume. I need to show that k is compact. That is, I need to show that k is bounded, and I need to show that k is closed. So, first let's show that k is closed, and I really need to take advantage of this assumption, which is about sequences. So I'm going to try to do everything I can to phrase things in terms of sequences. So let's suppose that k is not bounded, so I'll proceed by contradiction. So that means it's either not bounded above or not bounded below. Full stop. Without loss of generality, I will assume that this set K is not bounded above. There's a super similar proof if it's not bounded below. In particular, for every natural number n, could that number be an upper bound? Well, of course not. Oops. The set is not bounded above, so n can't be an upper bound. Now I have a sequence worth of things. Negating the definition of what it means for n to be an upper bound, I see that there exists some x sub n in K. Notice every natural number will produce a different element of K. That's why I'm calling it x sub n, such that x sub n is strictly greater than n. So I've just produced a sequence x sub n of elements of K. Let's see, the limit as n goes to infinity of n is infinity, and x sub n is bigger than n for every natural number n, so it must be that x sub n also diverges to infinity. But since x sub n diverges to infinity, that means that every subsequence of x sub n also diverges to infinity. I claim that this contradicts the assumption, which is numbered above as 3.10. Let's explain why, at least verbally. Well, what did I assume about this sequence? I assumed that, what did I assume about the set? I assumed that every sequence of elements of this set has a subsequence which converges to an element of the set. However, this is a sequence. This sequence, x sub n, has the property that its every subsequence diverges. So maybe I'll, instead of just saying, well, no, that's fine. So I've produced a sequence, x sub n, so that every subsequence of x sub n diverges. So this does not have a convergent subsequence. That contradicts our assumption, 3.10. So this set, K, must be bounded because I assumed it wasn't bounded and got a contradiction. Next, let's prove that K is closed. So, let's do it. Let's let P be a limit point of K. I want to show that P itself is in K. By the sequential reformulation of limit points, I see that P is a limit point of K. I want to show that P is in K. Because P is a limit point, I can use the reformulation of limit points to see that there exists a sequence x sub n such that for all n in n, x sub n is in K, but is different from P, and x sub n converges to P. All right, well, check it out. At the very least, x sub n is in K for every natural number n. So x sub n is a sequence of elements of K. So I can use assumption 3.10 to conclude that there exists a subsequence x sub n sub K such that x sub n sub K converges to an element of K. Oh, neat. So, let's just summarize that right here. So that means that the limit of x sub n sub K is in the set big K. I'm doing my best to keep my little k's different from big K's. Hopefully it's working. So this sequence, x sub n sub K, is a subsequence of a convergent sequence. Right, x sub n sub K is a subsequence of x sub n. And I know that x sub n converges to P. So x sub n sub K must also converge to P. So let's get our conclusion because, well, we're basically done. So what do we have? I know that P, as P is equal to the limit of x sub n sub K and the limit of x sub n sub k is in the set big K, it must be that, actually that sentence I think is not necessary. Because P is the limit of x sub n sub k, and x sub n sub k is in the set big K, P is in big K. So I started by considering any limit point of K, right? Let P be a limit point of K. I concluded that P is in K. That means that P is closed. Thus, K is closed. So since the set K is closed and bounded, it follows that K is compact. Nice. So remember the results from this video. This will complete the first half of this talk through of this packet. I'll talk to you again in a moment.